Today we're going to talk about microservices in Seedtag, how they are doing them, and Maximo is going to explain. Is a pet project, Maximo, or?
Yeah, it's a
or is a real business project?
No, not right now. It's not side project.
Okay, he's working on a side project for infrastructure as code, and he's going to explain what he did. I want to thank Seedtag for everything, because they put the place and they put the pieces that are coming later and all the beers and all that. And Autentia, as always, is recording it, so if you know somebody that can be interested about this, we are going to share the videos later. And that's it.
Cool, thanks. So thanks everyone, thanks for coming. Sorry for the technical thing here. Things always fail when you least expect them to, so nice. Cool. The thing is, I want to explain a bit how we're doing infrastructure, the challenges that we're tackling. Hopefully there's some things that you can take back and learn from here. Not sure, not that we do anything super special, but I think there are a couple of interesting points. So just quickly about myself, my name is Paul, I'm the CTO of Seedtag. I've been with the company since the very beginning. I took the CTO role 3.5 years ago, which means that that's the time that I've stopped playing with fun stuff and instead doing presentations and spreadsheets and stuff. But I can still talk about tech. So before I go deeply into the tech that we're using to solve things, I want to frame a bit the problem. I want to explain a bit what we're doing and from a product perspective, and then that will explain why we're doing things, how we're doing them. So, assuming this now works, I think your QuickTime thing, okay, it works, cool. I'm going to go a bit through an introduction about what we do at Seedtag, then explain from a 10,000 mile perspective what our tech consists of. And then from all that, I want to go into two specific problems which I think are very interesting. One is event ingestion, which we have a lot of, and our multi-data center setup, which is we recently, just 2 weeks ago, initiated. So I think there are some interesting learnings there. So Seedtag is in the advertising business, which I know every one of you loves, right? It's like best thing ever. Okay, no, the laughs mean that not. Why isn't that the case? There are a couple of reasons. Mostly, or the ones that are more recently, being tackled are regarding privacy. I think we all have that sensation where we're browsing around the web that we're being watched constantly. Okay. The idea behind of why ad tech is watching the users is actually good. So, I mean, the reason behind this is because the idea is that people want to learn, or machines want to learn what your tastes are and give you advertising that's somehow related to that. So that promise isn't bad. I mean, if I have to watch an ad, it better be something that I'm interested in instead of something that I really don't care. The problem with that is that in order for that to work, most of these companies are watching pretty much everything that you're doing. They're extracting massive amounts of information for you all over from the web, whatever you do, whatever you buy, which is a bit obnoxious from the privacy perspective. And you don't know what they're doing with that information. You don't know who they are reselling it to. You really don't control that. And the second problem with that is that the best that this can come up with is with this guy, which I'm pretty sure you've all had. Like, you're all being followed by that little ad from Amazon, right? With insert whatever you last search on Amazon with in that ad. So even with all that watching, with all that processing that people are doing about your activity, it isn't even so good. The result isn't even spectacular. What we're after is a bit different. What Seedtag is looking to do is, instead of trying to understand who you are, what you want to buy, your tastes, your race, your gender, whatever, if you have kids, instead we're focusing all that energy into understanding what each and every web page is saying. Okay, our idea is that if we fully understand what each web page is saying, we can serve ads which are contextually relevant to whatever you're reading at that point. You're already showing interest in, for example, cooking recipes if you are looking at the cooking recipe. So the whole point of all our technology is to understand deeply at a number of different levels what it's being talked about and to make advertising an extension of the content. We think that this is a better user experience because it stops following you all over the internet and only presents what you're interested at any given time. And the other thing that we try to achieve with our advertising is that instead of being this pretty ugly ads, we try to do things from a user perspective which are a bit more worked on. We try to have ads that are much more spectacular or innovative than what most of the advertising industry is doing, and also making sure that if you're not interested in whatever we have to say, we just hide the ad and get rid of it, so that you continue to see the content with it advertising interfering in your experience. Okay. So the whole point of this is. We've been now in the industry for 5.5 years. We started out like 6 dudes in a building over there with a couple of other startups. Today we have 7 offices in 7 different countries. We work with some of the biggest publishers in each of the countries. And the ones in Spain, you probably know them: Marca, El Mundo, El Confidencial, La Vanguardia, the big ones. In each and every country, we work with the very biggest publishers. So you've probably seen our ads at some point. I hope they weren't too disturbing. And yeah, that's a bit the point behind all of this. Now, onto the technology. How do we do this? By the way, I didn't say it. If you guys have any questions of anything that I am saying, just feel free to ask. I mean, just interrupt me. Okay, so to talk about the technology, let's first see the real challenges that we're facing from a technical perspective. First thing is, as I mentioned, we work with the biggest publishers in each of the countries that we work in, what we do is that we give them a small JavaScript tag that they paste on every web page. It loads for every impression, and what happens then is that this tag at least does one call to our servers. So in a sense, we accumulate the traffic of all of these publishers in our APIs. That makes about 20,000 requests per second on average. The second challenge that we have is that we're trying to influence the loading time of the page of the publisher that as least as possible. This is from a code perspective in the code that runs on the publisher, and also from the API perspective. We try to be as quick as possible to not, take up as least resources as we can on the publisher's side. So the target here is about 7 millisecond response time in the main endpoint that we use for ad serving. Finally, because we're not working in an environment that we control as we would when we're working in the browser, I mean, that's a hostile, a kind of hostile environment, because we're loading on the browser, which we don't control. We're working on the publisher's side, which are environments which we don't control. We don't know what the publisher is doing on their website. So we have to measure very aggressively to understand if our system is working, because it's not like we can install Sentry on the publisher's site. That's not going to fly. So we have a very powerful event system that pretty much measures everything that's related to how our ads are performing and sends it over to our servers to process that and to understand how we're performing. Okay? So that takes up to about 200,000 events per second. I'll go into that a bit later. Now, how are we tackling all of this? Obviously, like pretty much everyone these days, we're 100% cloud-based. We're using Google Cloud Platform. We started out when the first company first started. We started out in OVH. I'm pretty sure you know them. Bare metal, pretty lame service. And the problem with that was that we had to be doing capacity planning constantly for everything, because of the scale that we were growing at. And cloud, in a sense, is making that a bit easier. We don't get rid of capacity planning altogether, but it's much more manageable. We're now in 2 regions, so 2 data centers, one in Belgium, the other one in Sao Paulo in Brazil. And we work mostly with self-managed services wherever we can. This is because of a couple of reasons, mostly pricing related. For example, if we used as an example the events, if we were to, I did this rough calculation, if we run those 200,000 events per second through Google Pops Up, which would be their message queue, that would add up to, I think, 30,000 euros per month, which is a bit too much just for events. So in that case, we're using, for example, Kafka. In those cases where it makes sense because it's not differential that we do it or it's not super expensive, we do use Google's managed offerings like Google Container, Kubernetes Engine, Dataproc, or BigQuery. A bit about our software stack. So we run full in Kubernetes, GKE as I mentioned. Our main language is TypeScript. We do use Python as well. Python is all, but just relegated to those parts where we're doing machine learning. So if we measure this from a lines of code perspective, the big majority is TypeScript. We started out with JavaScript when we wrote our first microservices. I think after 1 year or something, this had bitten us a couple of times because of not having a proper typing system. So we had been trying TypeScript and Flow a bit earlier for all these microservices, but they weren't ready at that point. 1 year later, we came back and it seemed more feasible. So we started to migrate one by one all of our microservices over to TypeScript. The cool part is that as these microservices are micro, they're fairly easy to incrementally migrate. So you don't have to do it all at once. So it was a very long period where we were just rewriting them as we touched them. And yeah, today everything is TypeScript in our backend. We have 60 deployments, which means 60 different microservices, spanning obviously a lot of things within the domain. About 500 pods running at any given time. So this is 500 instances of those 60 deployments. And we try to avoid stateful workloads, in Kubernetes because, well, again, even though the latest versions of Kubernetes have been doing some work regarding stateful workloads, that means, by the way, databases, that kind of stuff. If your machines can be restarted every once in a while, it's not fun to lose your main database. Even if you're ready for failing over, it's not fun to lose your database every once in a while. So we try to avoid that. A couple of tricks that we're actively using to save a bit on the bills at the end of the month, because we do pay hefty sums for this. We use very aggressively preemptible VMs in Google Cloud Platform. Preemptible VMs, for those of you who are on AWS, are similar to the Spot instances. So they cost a third, I think, of what the normal instances cost. But you don't have any kind of guarantee that you will be able to keep that instance. That means Google is going to remove it from you without further notice. So you have like 30 seconds notice from the point that they decide they want to remove it from you. And an instance is going to last at most 24 hours. After 24 hours, it's just going to disappear. Okay. The cool part is if you're using Kubernetes on top of this, Kubernetes will mostly take care of this in the sense that as you're going to lose one instance, it's just going to migrate that workloads to your other nodes, or it's going to pull up another machine if it's needed. So it's pretty transparent, and mostly if you're not using stateful workloads, you just don't care. The second part that we've in this case we've had to develop is that Kubernetes is extremely happy to scale up the number of instances as you start having more and more traffic. The problem is that after, if you have a spike in traffic and then the spike ends, Kubernetes isn't so keen to, get back down those instances. I can imagine why Google wouldn't want to fix that. So in your own clusters, you can take care of that because it's a parameter within one of the Kubernetes services. But within GKE, you can't actually change anything of the setup. So what we did is, this is a very ugly bash script that will just every once in a while ask for the status of the whole cluster, see the utilization. If it falls below a certain threshold, it will just kill a machine. Okay. That way, that's pretty stupid, but I think we managed to save like 20% of our compute costs just by that dumb script. One day, I'd like to migrate that to a controller in Kubernetes, like do the fashionable way, but right now it's an ugly bash script that just works. So yeah, just in case any one of you is doing GKE, you could save some money with this. Now, deployments. How are we deploying those microservices? Obviously Jenkins. It's a hosted Jenkins. We have a continuous deployment pipeline, which means that there are no staging and no dev branches in our repositories. There's just master. Every feature branch is pulled directly from master and then merged directly back. As soon as you push master, that triggers the deployment into production immediately. What we do is that we have a standardized deployment, so there's a Jenkins file within each service that will build the container, upload it to, well, run the tests. There's unit tests and D2E tests, and then if that works, it will just shoot the container up to the Google Container Registry and just let Kubernetes know that it should update the deployment. So fairly easy, works great. And the cool part of this is we do about 15 to 20 releases per day with a team of 14 people. So it's agile. I mean, it's kind of easy to get stuff into production. So we're pretty happy with how that works. No fancy, we're not doing any Helm or stuff, which at some point we would like to do, but not yet. Not needed in any case. Briefly on monitoring, we use Prometheus and Grafana. We have a shitload of Prometheus graphs. We monitor pretty much everything. In the SDK that we use within all our apps, we have like a small custom SDK that all our apps are based from. We include, so kind of batteries included SDK for monitoring. So it has a couple of things, but it makes it very easy to start monitoring your app. So there's no excuse for any developer to not monitor any new feature that they add into production. So we monitor very aggressively both application level metrics and obviously system metrics like what would you get with Node Exporter, with Grafana, with Kafka, all that kind of stuff. That goes on into Prometheus. Cool, so that's about the 10,000 mile look. Anything you want to know about the infrastructure itself? Any questions about that? If we can tackle them now. Nope. Cool. So let's go for event ingestion. So as I mentioned, there's a lot of things that go on outside of our control. These are in the publisher, in the browser. They are in the publisher's website. So we have to rely on our own event system to make sure that we understand how the system is working. Okay. So what we do is that there are a lot of events that we launch at different points in what we call the ad server flow. Okay, the ad server flow is since the user goes into the web page until he has left that web page, ideally having seen an ad. So there's all kinds of events. For example, our tag was loaded on the page. We found an image within that page. We requested an ad for it. We found an ad for it. We rendered it. The user saw it. He clicked on it. Whatever. All kinds of interactions with all of our ads. To all of these events, we add a number of dimensions, obviously, which make it easier to slice later that data. So, what website that was in, the device type. So, if it was a mobile device, if it was desktop or something, the browser OS, the country where the user was coming from, whatever. A couple of dimensions. Now. This obviously, all of these events are triggered from the code on the website. So, and they're fired against one of our services. Okay, so they pretty much end up doing something like that. Imagine that this is, if we had a kind of a log of what was coming in. So imagine there was a tag loaded on page from website A for a handled device. Then a bit later, another one from a different website, and you have this big stream of events which individually don't actually mean anything. So they have no real business value if you look at them, isolated in an isolated way. We have to do something to be able to extract some kind of meaningful business data, something we can use or something that we can use to understand if there's something not working. So our ingestion system, pretty much what it does is reduce dimensionality. So for example, imagine that the time, in this case, I've truncated it to the hour, not even the second or the minute. And it's counting how many occurrences happened of a particular event, a particular time with a series of dimensions. Okay, pretty basic dimensionality reduction or counting system. So this is what this system looks like. How we're tackling it. As I mentioned, this adds up to about 200,000 events per second. So even though it's a pretty basic thing, it does require a lot of computing power to get that working. Okay. So the idea is as follows. We have the backend which receives these events. We call it the event service, super original. And then it does a very basic testing, making sure that everything that the input, as this is a kind of user input, we make sure that it's sane. We feed this into Kafka, which I'm sure pretty much everyone knows what it is. But just in case, it's just a message bus, which is super high performance. For me, it's kind of like Redis, the Redis of message queues. I mean, It's super easy. It scales linearly just with adding more machines, and it's great to work with. It has served us well. For these 2,000 events per second, we actually have a 3-node Kafka cluster, so it's like it will scale forever if we add more machines. This then feeds into our Apache Spark cluster, where we have a couple of tasks running, which will just take these events from Kafka, do this with dimensionality reduction, and then once they are compressed and grouped by, it will issue a couple of update statements to our MongoDB database. Okay, so it just converts all these individual events, groups them together, and then does updates to MongoDB, just incrementing the appropriate counters. It's set to observe true in case that it's the first event of that kind that's coming in, so that it will create the row. But basically, that's it. It will just issue increments to the database, to all those counters. So this approach has a couple of disadvantages. In no particular order of importance. First thing, it's not idempotent. As we're issuing increments to the database, that means that if for some reason a computation has to be retried because a node is failing or something, this will increment. It could increment counters twice. So you cannot rely on the data being exact. Not a super big issue because it's largely stable, but still, if you're trying to rely on that data being, precise, not the best solution. Also, Spark is pretty much overpowered for this, so you can do very, complex things with Spark, with joins of streams and stuff. Here, I'm just counting stuff, and the problem with that, so it's a bit overpowered, and it's a bit, difficult to troubleshoot sometimes. It's a complex piece of software, and sometimes, especially when you're trying to scale it and you don't know what's failing because you're hitting some bottleneck, troubleshooting that is a big pain in the ass. The second problem that we have is actually a bit more obvious. It's that MongoDB isn't a BI database. Okay, this was done on top of MongoDB, because we were 5 people and we didn't want to maintain these big, BI databases. We just had a plain, simple MongoDB database, and it was like, hey, let's just put it on that database too, because we only have one, and we don't want to maintain a second one. So it was just a commodity thing. The problem with that also is that the type of workload that I was explaining is a very update-heavy workload. So we're incrementing counters all the time. That's a kind of workload that MongoDB isn't actually really suited for. So what we're starting to see is that we're hitting lag spikes just when traffic starts to go up. So it's even starting to fail on that front. Also, as it is not a BI database, and pretty much no one in their right senses would use it for BI, unless I'm not counting just us. The problem is that it's not so easy to extract data for BI purposes. No one, or close to no one, is developing BI tools to work on top of MongoDB. There are much better options, starting with MySQL, for example. So we're on our own here, and we've had to develop pretty much every business BI capability on our own. So that's not cool, because there are a lot of very cool tools out there. And also, as it is a very basic system, it's missing a lot of advanced features like merging of different intersection counting or unique counts, all that kind of stuff that you have today in BI databases. Now, go back. There you go. With that said, we did this like 3.5 years ago, and it's seen an increase of per 100 maybe events per second. So even though it's pretty lame of a system, it's worked as well it's brought us here. So we've been, I think we were developing that. We had made like 1 million in the year in revenue, and we're now like doing 30. We're going to do 30 now. So it's seen a big, it's been with us for a while. It's worked, and it's only recently started to really fail. The thing here is, the takeaway for me is that at low scale, pretty much anything will fly. I mean, even a simple text file would probably do you well for a couple of time, for a lot of time. And in this case, even this pretty lame approach worked for some time. Cool. But like about 6 months to 1 year ago, we knew that it was starting to be time to change this approach and do something a bit more interesting. So we started to look into different BI, open source BI databases and not open source BI databases to make this approach a bit better. These are some of the usual the suspects. Pinot, especially ClickHouse now has it's making a lot of noise because there are a couple of big companies like Cloudflare using it. We know the other ones, we've tested some of them, we know how they work. But after some research, we've settled on, or at least for now, we've settled on Druid. Not sure if you know how it goes. I'm gonna explain a bit how it works because I think it's a very cool piece of tech. Now, Apache Druid is a very strange mix between an OLAP and a time series database system. Okay, it combines compute and storage into one system. If you guys have worked with ClickHouse, for example, that's kind of the same approach. We're just instead of splitting compute and storage, like the approach that we were using, which with Spark doing compute and MongoDB doing the storage, they're just all combined into one system. That allows it to do a bunch of pretty cool things, or pretty cool tricks when both are aligned or together. It's designed for high cardinality and high rate of events. It comes from an ad tech company, by the way, called MetaMarkets. So in our case, going through the documentation, they were obviously tackling the same challenges as we did. So it's pretty much designed for our use case. So that was amazing. It's like, hey, they're doing free work for us. Like if we had to develop something like that, it would have been that. So it's very specific for very high rate of events, of individual events, and when you're trying to do the same thing, where you get these individual events and you're trying to count them and reduce that dimensionality. Especially if you don't care about the individual events, as I was mentioning, if you just throw away the event after the fact and you just want to know the counts, okay? And it's extremely easy to scale. You just throw in more hardware, and it will just scale. I'll go a bit into how it works because it's a bit interesting. Druid is split into a couple of different services, kind of microservices. Okay, so the whole system, it's not just one process, it's a couple of them. So how it works is that you have the first process, which is called a middle manager, which will connect to a Kafka source and start reading the data. As it starts reading as each row comes in, it will just maintain a structure in memory, which is just the different dimensions that it has seen, and it will increment the counters on the fly. Does that make sense? So it's not storing the individual rows, it's just storing the counts, and as any new event comes in, it tries to match if there's a row which already matches all dimensions, and increments the count if that's the case. If not, it just creates a new row. Okay? So it will keep doing that until a fixed amount of time has passed that you can configure, or that the amount of aggregated rows reaches a certain threshold. When it's yay big, then it will just do the following. It closes that segment, okay? So it freezes it, and it uploads it to Google Cloud Storage, or to AWS if you're on Amazon. So it launches a signal to the system and says, hey, I've just finished this segment, I'm uploading it to Google Cloud Storage. And then at the same time, it creates a new segment and just keeps doing the same thing again. Okay, so it creates these new segments all the time, counts events within those segments, and uploads them to Google Cloud Storage. That's all it does. Once, while this guy is doing his job, as soon as this upload is finished, it will trigger a signal to the rest of the Druid cluster, which will be picked up by another type of node, which is called the historical. The historical, its only function is to pick up that signal and download the segment to its disk. Okay, that's all it does. And then it provides a query interface in front, which you can use to do queries on top of those segments. Okay. The final piece of the puzzle is what they call the broker. And now a broker is the actual interface that you as a user are going to use to query the system. It provides several ways to query things, but its function is as follows. It's connected to a metadata store where it stores who is in charge of which segment, and that segment, what time span is included within that segment. Okay? So when a query comes in, queries always have to go on a time like it's like the primary key is always going to be time. always for Druid. So when you issue a query and you have indicated a time, it will know which of the different segments contain information that is within that time. It will then fan out a couple of requests to both historicals, which have the frozen segments, and to running middle managers, which have live segments, which are still being written at. It will then combine the results of all of them and then give that back to you. So the cool part is you can query the data in real time, so it's just being updated in real time, and you can also query very large historical data. Okay. This approach, it's a bit of a pain in the ass. I'll talk about it later to have that many moving pieces. But the cool part is you can scale them individually. So if you have like a very big historical backlog, like you want to go back, I don't know, months, years, whatever, you just can add more historicals. Or if you need more power to query those that data. Just a second, because I'm losing my battery. ¿Tenemos cargador? Es que no me llego con este. ¿Alguien? No es USB-C, son los antiguos. Sí, okay. Yeah, so I was saying. So if you need to scale the historicals, just add more historicals. If your problem is not with the storage, but more of I have so many events coming in that I need more power to process those, you just add more middle managers. So it will just scale however you need. So it's basically the same argument as when microservices, okay? So same thing. But that's very, very cool. Things that work well with where Druid excels. As I mentioned, when you're doing a fast occurrence counting, that will, like we were saying, with a necessary time component. It's also ideal if you don't need low latency updates. So if you have to imagine that you're going to go back and you want to update a row of a frozen segment, that's not possible. What it will do is that it will invalidate that segment, copy that segment with the updated data, and then create that new segment. So it's not okay. It's not good if you're going to if you need those updates with low latency. But in our case, for example, this was not the case. I'm not going to update the amount of things that happened in the past, so I don't care. And finally, if your reporting queries that you need are mostly aggregating by several dimensions and getting back conclusions of these counts, okay, that's where Druid excels. Things where Druid is not so good, or things that we see as potential problems is, I've talked about 3 processes within Druid. It has actually 6 processes. Sorry. So there are 6 types of different microservices within Druid, and on top of that, it has 3 additional dependencies which are not managed by Druid, which are the metadata store has to be a MySQL, so you have to manage a MySQL yourself. You need Zookeeper to keep the cluster state. And you need the cold storage, which in this case was cloud storage, but you can use HDFS or something if you are using already a Hadoop cluster. But it's in total, there's like 9 moving parts, which make this a bit of a complex system. This contrasts heavily with, for example, with ClickHouse. ClickHouse is just a single process and Zookeeper. So you just have 2 types of processes, which is less. Second, because there are six different processes, and it's based on the Java virtual machine, you have to do the tuning of 6 different Java processes. Which, if you've done it, it's difficult depending on your workload. And I'm sure we'll come up with a lot more problems as soon as that is in production. The state of that right now is that we have our Kafka cluster, and we have our Spark cluster on one side, and our Druid cluster duplicating the same data, so doing the same processing twice. We're doing that kind of an A/B testing to see how it scales, if it has bottlenecks, and how it compares in performance with respect to our current system. We hope at some point soon to just get rid of the Spark cluster and go for Druid finally. That's about what I had to say about Druid. And just one final area which I wanted to tackle is how we scaled from one data center to a second data center. This is highly workload specific. I mean, it's going to depend a lot on your business domain, on the data you have, and your own problems. But maybe there's some learnings here that could be interesting. Now, The reason why we started doing this is because we have markets in Latin America, and initially it wasn't justified to do any specific work for them because they were like very small markets. But we hit a point where the fact that they were so far away from our data center, which is in Belgium, was adding so much latency that it was actually impeding that the KPIs were better and that the business would grow there. So at some point it was big enough that it was justified to open a data center there to improve their KPIs and to make everything go better. So that was the first case objective that we set for ourselves. We wanted to reduce latency, or we had measured that there was a possible impact of reducing 1.6 seconds for every ad rendering for each user. And that doesn't sound like a lot, but 1.6 seconds in our business is like eternity. So big win there. There were obviously more KPIs that would be impacted by this, but they don't make sense here. And this more technical objective is that we wanted to structure this in a way that we would have to duplicate as least infra as possible. We're a small team. We're 13 people now, and 14 people now. And the problem is we don't want to manage everything twice. That takes a lot of effort, and especially if it's on the other side of the pond and the time zone is not the same. So we wanted to have as much as possible on our main data center. What does this mean? We wanted to only have that in that data center, the real minimum services that would be needed to serve ads. Nothing related to analytics, nothing related to billing, nothing related to the machine learning stuff, nothing of that would be there. There would be only the minimum services that would accept a request from the user and give back the necessary information so that the user can render an ad and see the ad working. Okay? Now, this is like very simple mock-up of how the service works. Once the tag is loaded on the page, the thing it does is it sends us, it connects to our kind of a gateway service, and it asks for, hey, what's the information that I need to be able to render an ad on this page? This gateway will then spawn a couple of requests to a number of different services, and will then compose the responses back into an object, which it gives back to the client, to the user on the browser. Okay, pretty simple setup. Now, the cool part here is that, or one of the key things is that as part of this flow, there's no single write that's going to be needed for this to work. So it's a read-only kind of flow. And that turned out to be a massive advantage. So that means that for these services to work, they need to have a copy of their data on that same data center. We don't want them to start jumping, over the pond for every request. So we need to bring the data close to them, but we don't need to manage in any way that they update that data and that we have to merge them back with our system. At least not in a synchronous way. We'll talk about events in a minute. So the setup ended up looking like this. We have, as I mentioned, it's MongoDB mostly. So we have the main MongoDB replica set, or most of and the read-write instance is on our main data center in Europe. It's set up to replicate this way and have only read-only databases. Okay, so in that sense, everything that could be a write here is not being performed. So it's only doing reads. And if you need to do a write to any of these services, there are copies of these services also in this data center. So if you need to manage that data, that's always going to go through our database, but it's not part of the main serving flow. It's more of if someone is editing something in the back office tool or something. Okay. This approach has also an additional advantage, and it's that this connection is not reliable. It can be cut off at any given point in time. But the cool part is that if this cuts off, this system will continue to work because it has the data locally. It's not having to jump to the other data center. And it can continue to work just fine. Maybe the only problem is that it will serve stale data until the synchronization is restored, but that's not a big problem in our case. And as soon as that connection is restored, it will just update all the data and start serving with updated data. The second part that we had to manage are events, which are the writes. So you remember this was our very basic write event ingestion system. There were only minimal changes needed to make this work with the system. What we did is that we kept this part, so the MongoDB, Spark, and Kafka on our main data center in Europe. we built a second Kafka on that local data center so that the event services are hitting that Kafka locally. Now, on our European data center, we have the Kafka Mirror Maker software running, which is just a very basic system that will act as a consumer of this queue and act as a producer in this queue. So we'll just basically copy data from one to the other. The thing is then that everything is flowing in there, and this just merged into the normal flow of the main Kafka, and Spark and MongoDB are just seeing the data as if they were coming from a single database. There is nothing from a single data source. Sorry. So we didn't have to do any changes on that part. Again, same resiliency things apply. If for some reason this connection cuts off, the thing is, event service will just start buffering these into this Kafka, and they will just not be updated on MongoDB. But as soon as this connection is restored, everything just comes in and starts being processed again. Okay, so this proved to be very resilient, and it's working fine for now. It's been 2 weeks since we've had this in production, and in 2 weeks there's been no outage. So cool. The final piece of the puzzle is how is a user connecting to one data center or the other. We're doing that with multi-cluster ingress in Google Kubernetes engine. If you know ingresses from Kubernetes, it's just getting a certain IP address to expose a certain service to the internet. Now, multi-cluster ingress does pretty much that. So it manages the same object that an ingress is managing on Google Kubernetes and Google Cloud Platform, sorry. So the same rules, firewall rules, backends and stuff. It's just managing the same thing, but it's assigning a single IP address to both data centers. Okay, this is a unique, an Anycast IP address. How that works is that the internet is pretty much a graph of nodes, which will make sure that your packet goes from A to B. If two different parties announce that they have the same IP address, what the internet magically will do is that it will create routes to those endpoints, thinking that they're actually the same point, but using the shortest path to each and every one of these. So if I'm a user in Brazil, the shortest path is going to lead to the Brazilian data center. If I'm in Europe, the shortest path will lead to the EU data center. So it's a bit of magic, but it works just fine. The cool part about this kind of approach of using an Anycast IP address is that failovers are managed by the internet for you. So the internet is designed to handle continuous failovers. So if your data center just goes down, it stops advertising that IP address, and the network protocols will just make sure that traffic is no longer routed to that data center. And this is done in seconds or in very short time, compared to, for example, another approach, which could be DNS. In the case of DNS, it could take minutes to even hours before a DNS entry is updated. So that's why doing DNS would not be a good solution for us. And yeah, that's all I have to say about all of this. We're obviously hiring, as always. Thank you very much. Hope this was useful. You guys learned something, took something away from this. And yeah, thanks a lot. Any questions are welcome. Yep, we'll not take a mic.
I have a small question about your Kafka setup.
Yep.
The three Kafka.
Mm-hmm.
I'm not very familiar with Kafka,
Mm-hmm.
but basically, why do you need 3 instances of Kafka,
Mm-hmm.
not 2?
Okay, it's actually 2 instances of Kafka, and the third Kafka is not actually a Kafka by itself. It's a Kafka Mirror Maker, which is just, let's go back. I lost it, sorry. It's here. There you go. So this guy here is a mirror maker. So it's not a Kafka per se, it's just a software that acts as a mirror. So it takes events that come in from one side and puts it into another Kafka. It's not a Kafka per se. It's just at the same time a consumer and a producer of data.
And you can configure the first Kafka at the top to be a producer to the third one?
No, just a Kafka waits for someone to connect to it and ask it for data. It's not. It won't. It doesn't have a push kind of functionality. It will push that to someone else. You use Mirror Maker for that.
Yeah, regarding the content that you serve on the advertising about the CDN, how do you manage the content of different data servers?
Sorry, how was this question?
CDN, how do you
oh.
manage the CDN?
Yeah.
It's the same for the events, quite related.
Okay.
But it's more really needed for the advertising.
Exactly. Yeah, so we're using, that's a great question. It's a bit complex because for every ad, there's like, we separate it into logic because our ads are not like basic images. They do a couple of things. They're actually small React apps, each and every ad. So they manage state and they use these transitions and we use React for that. And so the logic on one side, and on the other side, there's the creative part, so the assets. These are managed we use Cloudflare for that. So all the assets are stored on a Google store, Google Store, Cloud Store, GCS, on GCS and publicly exposed. And then we have Cloudflare in front of that, and it will just serve that. It's a bit more complicated, but I don't want to go because I have to tell a lot of stuff if I go into that. But the assets themselves are there. Actually, it's also a cool part of the system. I just saw our data for the traffic served of static assets in the last 30 days, and it was like 850 terabytes of traffic. So it's a ton of traffic that we serve.
And for handling, because you don't have cross-country campaigns that works all together when you launch it in different countries, and you need to change, for example, some assets, you need to validate on the CDN to use a human. Exactly.
For that, so the thing is, how it works, like all of our creatives are created within a tool with which we manage, which we call Seedtag Studio, and then the cool part is that we manage the whole flow. So I know when a user makes a change, for example, our design team, when someone from our design team makes a change to that creative, I know which one it is, and I just trigger an invalidation to Cloudflare and make sure that they invalidate that, and they will just make sure that every point of presence will invalidate that immediately. So, but yeah.
Thank you.
He was obviously in the industry, in the advertising industry.
So regarding the processing and storage of the data, you guys are now testing Druid against Spark and MongoDB.
Yeah.
And collecting metrics. Any interesting things so far?
So we noticed that. So we've been running that at the same time. It's so there's a bit. We're still like trying to figure out a lot of things of how Druid works or how it's gonna impact us. A couple of cool learnings. When you go to standard BI databases, you have a lot of very cool tools that you can use. Don't know if you guys have heard about Superset, Redash, Tornillo. There's a lot of very cool tools that you can use with that. So we're still trying to figure all that out. From a perspective of processing, we have, for example, we're right now managing is it 3? I think it's 5 tasks, so 5 middle managers ingesting the whole thing, which are 5 cores. So it's like if it was 5 cores just managing the whole flow compared to Spark, which is we have 8 machines in the standard 8 machines in Google Cloud. So it's more like 64 cores. So it's more effective also, or it's more efficient at doing that. And apart from that, when we extract the data, so we do queries, it's extremely fast. It's able to scan thousands of segments in milliseconds if you have enough hardware for that. And we have right now. So right now our setup is 2 machines hosting middle managers, and 3 machines hosting middle managers and historicals in the same machine, 8 core machines. And then the other components are on different machines, but I don't want to go into that. Cool. And yeah, so effectively, it's being much smaller of a deployment than compared to our Spark deployment. So it's much more effective doing that. And it's also much more powerful in the queries that we can do. So yeah.
You talked about the deployment with Jenkins before.
Yeah.
Do you do canaries or something like that, or just like everything goes?
We're a bit of a suicide people here. So the thing is, we launched them directly. The thing is, everything is monitored very aggressively, very, very aggressively. So if anything goes slightly wrong, we notice that immediately, and we can roll back very quickly. So you have the images in Kubernetes, so a rollback is actually instantaneous. We're more like that. instead of doing canary releases. Yeah, it works. I mean, if you have, we have a good test suite depending on some services, but we have a good test suite. And if that, Laura lost. So yeah, but so we tend to find things going wrong before that actually goes into production, but not always. But that's fun. I mean, it has to break every once in a while.
No fun.
It's life. Yep.
How do you scale the API? Do you use horizontal scaling? Have you tried serverless? Have you considered that?
Mm-hmm.
Have you taken a look at prices and other comparisons?
Okay, good one. I was actually, among the, how do you call that? Not very believers in the serverless paradigm. I'm starting to shift my thinking a bit regarding that, but still not super sold on serverless. We had already done all our microservices. They all expose APIs, and it's very easy to manage that. Once you get into that, into that role, I see lambdas or so as something that you can kickstart, gets you up and running quickly if you're just starting out. It's something to go, get fast into action. But later, I think you will always end up in a kind of microservices or monolith or your bigger approach. And we're past that in that sense. That said, we are investigating maybe the possibility of using lambdas, or we've thought about using lambdas for very specific tasks, but not for the API. That's all going to go through our current system because of costs. It's costlier. This price per CPU is costlier in the end, the processing, than in microservices. So for now, not for now, but maybe for specific tasks.
Just one more question because
pizzas over there. Yeah.
Yes, we have another talk.
Yeah.
After that.
Yeah.
Fine. But now we are going to be in the work.
Yeah, so we can talk about it later. Cool. Go.
About the events, it's a business requirement to have it on real time, because I see a lot of.
Yeah, it's big, right? Yeah. So it's like, yeah, I get it. It's not a business requirement. So Spark has a 1 minute delay. I can live with 1 minute delay. I mean, it's not bad. That was like a icing on the cake. That came for free. Okay, it was more of that. The real reason was that people had started to stop using the systems that we had built on our system, and were going for the database directly, to aggregate data, because the system was becoming very slow, and the tools that we had to develop were not very good. So it was more of make data more easily accessible, and allow people to query longer periods of data, which we couldn't afford with MongoDB. You tried to query for 15 days, and it would just stop. It wouldn't give back all the results. So it was more of that, and then the real time is just a nice extra.
Because I see the contrary pattern about doing this. I started saving all these historical data on S3, for example, and after that going to fetch the information that you really need, kind of structured information on S3, and after trying to stream.
Yeah, with Spark or something,
on the other case.
The other extreme. Yeah. Very cool.
Thank you, Paul. We are going to have later pieces so we can have more questions.
Yep.